So basically today is to talk about the intention for Scan-to-BIM. What I've did today is to break it down into two parts. So we talk a bit on this week with the fundamentals and introduction towards Scan-to-BIM, and next week I'll talk about a bit more how we can really do Scan-to-BIM, because we can hear a lot of people saying that I can do Scan-to-BIM, I can do Scan-to-BIM. I can tell you how they do it. It is not automated. It is always a manual, very laborious job. Okay, so I'll explain more on why we're doing Scan-to-BIM, and then we'll come back to the fundamentals of scanning, fundamentals of digital data, fundamentals of modeling, and then only then we go to BIM. All right. So as what Kunde said this morning is that this is part of our research project from the Royal Academy of Engineering. So it's sponsored from the RAN in the UK, and we're partnering NUS in Vietnam for this project. The essential key aim for this is to develop an open access e-learning platform towards digital skills for development in construction. So what we have identified is that BIM, as what everyone knows, is something that everyone wants to do. However, to do actual scan to BIM for existing buildings is a very big problem, which I will explain on. All right. So we asked the question of digital data. What we want to gather from any construction project, anything to do with BIM, is all about digital data. But when you get digital data, we get lots of information and everything else. But what are we going to do with that? Okay. When we design a new build, we all use different softwares. You use your AutoCAD, use Revit, whatever it is. It's all digital data. But what is this data used for? How is it being stored? And all these things we all cannot see. All right. And that's a problem. So there's a big process of collecting and acquiring digital data. We want to transform the physical world, what we have around us, the offices, the buildings, into the digital world. That's what we want to do. Okay. What BIM does and what a lot of modeling does is that we are drawing things in the digital world. Once we get to draw them, you want to put it in the digital world, then we can apply colors, we can apply materials, we can test, we can do simulation. That's what it is for. When we look into BIM, a lot of people say different things about BIM. Okay. Some people think that BIM is a nice 3D model. That is just a model. BIM actually is information inside the model, and that really what BIM is. BIM is not concerned on how nice or how beautiful it looks on the digital side of it. It is concerned of the information inside. So the preconception of what BIM is very important for us all to understand, is that BIM is a model in 3 dimension with the right information inside, and that's what we are looking for from now on. We're not looking for nice rendered 3D models that everyone can do it, but what we're looking for right now is actually information to put inside a model. And this research looks a lot on existing items. So for example, if I want to redraw my house, for example, to do some renovation in my house, I'll need to redraw it. How do I redraw my house in the digital world? And that's going to be quite hard. All right. Later on, I will demonstrate how do I redraw a little drawer, a small piece of furniture. That's how we're going to do it. Right, so what BIM is and what we want to do with BIM, okay? The key thing is this, is that all the information that you guys have in your models will be stored digitally in digital state. It's something we cannot see. How do you collect data? You can't see these things. It's all digital. We look at digital and analog and Morse code binary numbers, and all these things on the right hand side. You get the binary numbers. The key thing is that all this data we have can be in bit, 1 byte, megabytes, terabytes, and these data sets can go larger and larger and larger, and we look at how to manage this type of the data as well. Okay, so we asked the question right now, is that for digital data, how do you use something you cannot see? How do you store something you cannot see? How do you ensure the quality of something that you can't see? That's something you got to really think about, because when we do anything digitally these days in modeling, is that these are things that we can't see. How can you use it? Is it magic? Is it myth? We'll find out on a bit later on. Okay. So when we look at digital data, what is digital data? We want to ask the question. All right. So in terms of concept, or in terms of a quote. This is given by measurement computing. Where we're looking is a sensor. We get a sensor to give us a signal. Signal we transform it into a digital sense. Okay, we're taking something from analog in our world, what we're seeing today, change it into a digital signal and put it in the computer. That is what we want to do. All right, same thing. Here is that it's a process of measuring electrical and physical phenomena, voltage currents, and send it into a computer. So there's a sensor, there's a signaling device, and you put it in the computer. And this goes both ways. So the ability of changing our analog world into a digital world is what we want from BIM. Okay, if you want to design a new building, that's simple. We just design, we just model, put information in. That's your BIM gone. But for Scan-to-BIM, the key thing right here is that for different monuments, any historical items, which I can show you a bit later on, we need Scan-to-BIM, and we need different technologies to get it done with. Okay, there are a lot of methods to acquire data, how we collect data. All right, it is just a quick 6 of them. You have the slides, you can see all the links right there. But the key thing is this: is that all these methods of acquisition is expensive. All right, it is very expensive. Some parts of it requires very high-end hardware and so on and so forth. But for this lecture, I'm going to introduce 2 big parts of it, which is the laser ranging systems, the structured light methods. These 2 main technologies. Okay. Laser ranging systems will look at very sophisticated laser light. So what it does is that from Earth, it shoots out laser pulses to a satellite, it bounces back, and we get a point. Okay, so what this system does is that it does a very high-end laser shot from a center base anywhere in the world. You want to reflect off a laser satellite, and then you get a point down on the ground on Earth. However, this is a very quick way to have a digital map. That's what it does for. At the same time, is that it is very expensive to process. Okay, but this concept has been simplified to what we use in 3D laser scanning these days. I'll explain later. Next thing we look at is a structured light method. So this is a very simple method people can use, whereby I use a light and a projector to get data. All right. So there's 2 parts, as you can see. A camera will shoot at the object. A projector will measure the distance, and then when it shoots back, it gives you 1 dot. That's the point cloud. And what you could do is when you have multiple point clouds, then we have a very good 3D geometry. Okay. When we look at it quite carefully, this is a quick system. Anyone that plays an Xbox Kinect, for example, has already a laser scanner in the house. All right, Microsoft Kinect is one of the first mass market structured light depth camera used in 2010. This is one of the laser scanners. At the same time, those who have a product called Nintendo Wii, which is a bit year 2000, that uses about the same technology like a laser scanner. Okay, so all these laser scanning products are available in our homes right now, whereby if you look at the Kinect, you can get one's a laser projector, one's an IR camera, and a color camera, and that's how they can detect the game movement that you can see today. All right, so that is the structured light method. This is how it works. So line of sight is important. So the problem with the light method is that you need proper lighting. You need to do it in a very controlled environment. You need to make sure is that if there's a difference in lighting, you get different reflection. So to do this outdoors is quite difficult. Hence, we only have very large point cloud gap between each. So when you look at the Microsoft Kinect, point clouds will come back only at a 2 centimeter wide at the maximum. Okay, when 2 centimeter wide point clouds is not very useful when you want to do something very detailed. These are some other products that we have. So on the left hand side, these are the handheld scanners which we have in Manchester Metropolitan. It's a Faro one. You get the scan in the box. You can see 3 different systems right here: the projector, a laser, and a color camera. On the YouTube one, the scan in a box FX, and then you get one of the handheld ones as well. Okay, so all these scanners range between £5,000 up to £20,000. So again, it is useful, but it's still a bit expensive sometimes. Okay. Next thing, what we look at a lot is LiDAR. So LiDAR is the light detection and ranging. So this LiDAR uses a pulse laser. So same thing is that they shoot the laser out. They put a camera to collect your 2D image, and it bounces back. It creates a point cloud. Okay, that is quite simple. LiDAR generates very accurate 3D information. What it does? A laser will scan. It shoots towards a building, for example. Then it reflects back, and then you get a point cloud. Accuracy can be down to 2 or 1 millimeter accurate. And this is very useful when you are really scanning a heritage building, for example. Okay, the laser can be shot up to 400 meters as of today. I know that people from Leica Geosystems and all this, Faro, they are looking at further distance to be shot lasers. So up to now, 400 meters. So if you look at 400 meters one way, this will mean a single scan can cover up to 800 meters all around it. Okay, so we are almost approaching 1 meter, and this really makes life on site much more quicker, much more powerful. Two big parts of LiDAR. Terrestrial LiDAR will mean what's on the ground, what we can scan, what we can see. So now I'm sure you could see, for example, this is a power station which is being scanned. Different colors means different distance, nothing else. All right, it doesn't mean different materials, nothing else. So all these information you get back is all only in geometry, means how big, how long, and that's it, nothing else. Airborne LiDAR is shot from the sky, from planes, shot down and collected back, and you get a lot of terrestrial data. So all these things in airborne LiDAR is used in remote sensing. Okay, it's very powerful to collect data very quickly, and you can know what's wrong with the forest and so on and so forth. There's a lot of different technologies now put in airborne LiDAR, because they are implementing different imaging technology to look at crops, the health of the crops, whether is it disease or they don't have enough nutrients, and all this is being done via airborne LiDAR and imaging. Okay, LiDAR is also used in autonomous vehicles. So as you will know, we will be having wireless driverless cars very soon. And if you look quite closely in the driverless cars, there is a big sensor at the top of the car. It's a LiDAR. And this scans everything around the car and informs the car not to go left or to go right, go fast, go slow. Okay? There are also other cameras and sensors around the car, but the LiDAR provides the most accurate information based on what's around the car. So all autonomous vehicles, look at the top of the roof, the things that turn, there is a LiDAR. And without the LiDAR, the car cannot perform properly. Okay? Autonomous vehicles works on both sides. You need the LiDAR for the information, as well as the GPS, so that it can know the direction of where for it to go. Okay? LiDAR, again, in remote sensing, I did mention. To my friends in surveying, it's a game changer. As I said, one scan now can go up to 800 meters. In the past, it only go for 200 meters. So one scan is now equivalent to 4 other scans done in the past. And with this LiDAR scanner is that we are using LiDAR scanners to scan buildings. I can show you some demonstration later on. Okay, so land surveying right now, they don't do it traditionally. They don't do the contours. They collect data, digital data of the surveys, what they do it, and then they will come back to the office and regenerate into a larger piece of work. So even the surveyors in land surveyors are collecting digital data. These are some product examples that we have. On the left hand side, this will be the Leica P40. This is what we use in Manchester Met. We have good relations with Leica Geosystems, which we can play with. So again, this is the scanner that can provide scans up to 400 meters each way. You look at the hexagon arm. So this gives a very precise scan. So this is for precision engineering. This scan can draw up to 1 nanometers. Okay, the scan on the left, the Leica one can go up to 2 millimeters. This is up to 1 nanometer. 1 nanomillimeters. So it's very, very precise. And this is what we use in scanning in the car. So wider space, and this is what we use. Okay, so there's a few links up to there. You can have a look at the products that collect digital data. Another way to collect digital data as what we can use of is photogrammetry. It is quite a popular tool because of all our mobile phones today. What it does is that it uses photos, normal photos, to generate 3D images of a project, of an object. Okay, there are few technologies being used into it, but if you have a very powerful smartphone, go to App Store, go to your marketplace, search for photogrammetry and app. It should be, you can get it for free, and you can try redesign your model using photos. Okay, so photogrammetry will mean light drawing measurements, so it's photogrammetry. That's what it means. It's how it looks like. This is a quick print screen. If I want to model a tree, a bark of a tree, if you can see, this software, I will take pictures using my phone, and then the phone around the tree, all the blue dots around the tree is one picture. The one highlighted is the one in pink. When you take all the pictures around the tree, it collects the data. So you get one very nice model. Okay, that is your 3D model. That's all. Or you can put it in the lab. This is how it will look like. Okay, cameras everywhere to get a good photogrammetry model. Again, when you look at LiDAR photogrammetry, it can be combined. So there's a lot of talk now of having drones. So drones uses LiDAR to take photos, to take the scans. At the same time, we have also tried photogrammetry in airborne remote sensing. Both have different pros and cons. For example, the photogrammetry stuff is a bit cheaper. What we need is a good drone and a good camera. A good LiDAR means you need $50,000 just for the sensor. All right, and a good system is expensive, so up to $300,000. Photogrammetry is easier. There's no sensors. You just need a camera and off you go. While LiDAR will need georeferencing. What mean is that it needs a bit more GPS installed in the sensor as well. If not, it wouldn't know what is it scanning. I will explain to you the problem of scanning later on. The outputs of it is very different. So you get in photogrammetry, it's only on 2D and 2D maps and 3D models. That's all, nothing much. You don't get very accurate information. Say 1 centimeter horizontal to 3 elevation. What we need is elevation, vertical, which is more accurate within the LiDAR systems. And photogrammetry usually we use for mapping. Quite generic things you want to do, nothing more precise. If you look at the photogrammetry, is something more detailed. So we're looking at a very detailed plan of everything. So LiDAR photogrammetry can work if you want to collect digital models, but if you need something more precise, more accurate, you need to go to LiDAR systems. Okay. So why are we doing all this? We ask a question. Why do we want to do Scan-to-BIM? Why do we want to recreate our analog world? Is that what we want to do is to have a digital twin. All right. In the UK, we have a lot of existing buildings, and that we cannot demolish. Then we need to refurbish. So to allow us to refurbish the building in a more efficient manner, we need to have a digital twin, because we need to model energy, we need to model daylight, we need to model a lot of things within the building. So with a accurate digital twin, we are now able to perform any refurbishments, any retrofit, anything else with more confidence. If you don't have a digital twin, it's hard for architects and anyone else to work on the building itself. Okay, we ask the question, why, before we do a new build, for example, why do you want to have a BIM model? A BIM model is a digital twin, but a BIM model as a new build is much easier to draw. What we have in the digital twin is that we have the accurate representation of an existing building. Okay, a physical systems, a real digital copying of the physical systems to perform real-time optimization. That's what we want to do, optimize everything else. Another concept of digital twin for NASA and US Air Force is that they want to integrate the physics, the probabilistic simulation, and everything else, the modeling, every sensors, everything else back into a model before they put it up in the air. All right, that's very important. So when we look at pilot training, for example, that is one of the best digital twins that we can find. All right, this is because pilots train at the simulator, and this is what it happens. If we all play games, for example, these days, anyone plays Grand Theft Autos, you can drive your car on a Formula One track. The Formula One track is a digital twin. All right, whereby when you play the game, you are as though driving the car on the track itself. That's what it is, a digital twin, so that you can experience what the real thing is. If we can bring this experience to a construction/engineering environment, we can then now do proper simulation so that we get it right first time. Okay. Remember that in Europe, in the UK, our regulations are very strict. We have very limited time to do work on site, and sometimes the site area is very small. So we got to make sure we get everything right. Having a digital twin allow us to do that. Even have health and safety training before they go to site, because why? We can show them the site online and things like that. Okay, so digital twin, you can hear a lot of this. This also hits off towards Industry 4.0. Some would say it's Construction 4.0. So this is what we're working at. So Scan-to-BIM is like a digital twin. So this is what we see. So those who have done laser scanning before, you will see like this points in the air. However, we ask the question, what are the points? Okay. So laser scanning is the most efficient tool to collect spatial and geometrical data. What it means is that it just collect geometry, the shape, you can distance, that's it, nothing else. Okay. It can be accurate up to 2 millimeters, and it can be collected in terms of X, Y, and Z, and L, which is the coordinates, and L will be the information collected within the point itself. Okay, I'll show it to you. So again, these are the main equipment for laser scanning. So what's in the middle is something quite new, handheld scanners. We are trying to combine data collected from laser scanners to the light sensors, and so combine all the data together, which allows us to do a much more detail into it. So the advantages of laser scanning is that, as I said, is geometrical information, is very accurate. You can inspect data from various points. Technically, you can fly around it. It's a non-contact data acquisition, meaning you don't have to touch the item. So if you go to heritage, you go into, for example, you can even scan a picture or a statue. You don't have to touch the statue. You can just scan it and you get the data back. And the key thing is it reduces time on site. So when we look at the nuclear industry, again in the UK, we use a lot of laser scanning. Okay, what we've done in the past is that we've combined a Connect sensor to collect laser scanning, put it on top of a remote control car. Okay, why we're doing this is that there are parts of the nuclear site that we cannot enter, and we do not want to spend lots of money to create a robot and put a £50,000 scanner on top of it. So what we did there is to have a geometrically sensitive remote control car, put the laser scanner on top, and we scan parts that we cannot go in. And it depends on the gigameter at that time, if you can reuse the remote control or not. If not, we just leave it inside. So that's one key thing about laser scanner. We can see things that, through robots, that we don't have to see it out on ourselves. Disadvantage of laser scanning, there is the line of sight. So basically, you can only scan what you see. So if you scan something from the front, you cannot scan something from the back. You need to go behind it and rescan it again. These provides you with different scan data sets, and these data sets can be very large. So it depends on what scanner you use and the intensity. Each data set can be as big as 1 gigabyte. Each scan, you got 10 scans, 10 gigabytes of data. A lot is overlapping. What we're going to do about this depends on your computer, how powerful it gets. Okay. Point clouds by itself is meaningless. So when you generate data back and you get back the points, it is meaningless. It only have X, Y, Z, and L. To you and me, it's meaningless. Okay, but to the computer, it must be meaningful, because it serves no purpose later on. Okay, equipment can be expensive. The laser scanners. At the same time, if you skip stitching of the scans, can be quite hard work, which I will show it to you later on. Okay. So there are not one system that is perfect, but in laser scanning, what we're looking now is that there are the advantages right here and the disadvantages right here.